Okay, I just wanted to take a few minutes and sort of encapsulate where we've gone throughout the semester. I was looking back as I was preparing for the final exam, and just wanted to give you sort of the bird's eye view of everything that we've covered. Looking back, we spent a massive amount of time on Chapter 1 on the mathematical foundations of quantum mechanics. That was a large number of lectures that we spent on that, but I don't think I regret it actually, because I think now I have a good sense that we have a common language to discuss linear algebra, simultaneous diagonalization, degeneracy, all of that stuff. So maybe a little bit of this could have been trimmed, but I really wouldn't change all that much. We spent a significant amount of time as well discussing the properties of classical mechanics. So it took quite a bit of the semester before we even really dived into quantum mechanics proper. But as you can see, the way that we sort of jumped around a little bit within the textbook, the main theme that we were hitting with classical mechanics was not so much Lagrangians per se, but symmetry transformations and Noether's theorem, so that we would have a solid foundation for what a symmetry transformation is and how that carries over to quantum mechanics. This is something that Shankar does, but it's very disjointed. That there's some of this discussion of symmetry in a section in Chapter 2, and he saves the big discussion until much later in Chapter 11. And we decided to hit that right off the bat. Then we addressed the transition to quantum mechanics after 11 lectures of discussing linear algebra. I was sick of it and wanted to talk about quantum mechanics. So we did the Stern-Gerlach effect. And then we talked about the postulates and canonical quantization. And then really, it's only been in that last portion of the semester that we've dived into quantum mechanics really proper. Shankar, for reasons that are unknown to me, decides to save the general treatment of the Heisenberg relations until much later in Chapter 9. We hit that early on as part of canonical quantization and the approach to quantum mechanics. And then we discussed the free particle, time evolution of a wave packet, the propagator, the classical limit and Ehrenfest theorem, and then we apply this to solve simple problems in 1D. The free particle, scattering off a one-dimensional barrier, bound states, and then, of course, the most important of those one-dimensional problems was the harmonic oscillator. And then this last section, the last few weeks of the semester, have been dedicated to rotational symmetry. Rotations in 2 dimensions and angular momentum. Last time and this time, rotation in 3 dimensions. And then I want to cap off the discussion with a talk about spin. I fully anticipate that I am not going to make it all the way through my stack of notes here by the time we end our hour and 15 minutes class today. But honestly, I've been looking forward to this discussion of spin the entire semester. So I am going to keep the video rolling, and I'm going to keep lecturing until I am done. Consider that time after the hour and 15 minutes is over as for fun. Nothing on that is going to be on the final. You will not be expected to repeat that back to me. But this is where we have been aiming the entire semester, to understand symmetries, their consequences, and how that applies to very abstract notions in quantum mechanics like spin. So I really want to stick with this long enough to deliver on that promise. Okay, I am almost finished writing up the final. I should be on track to have that posted for you guys tomorrow. I think right now it's looking like a 3-problem set comparable to 3 homework problems. And I've tried to choose those problems in a way that will synthesize various aspects of this whole discussion. So I think that's all I have before we get started. Do you guys have any questions, comments, or other concerns for me? Okay, if not, then let's see how much ground we can cover and whether we get into spin before we get into overtime. I was also not expecting the chalkboard to be this dirty today, so please tell me if you can't see something and I'll try and figure out what I can do about it. All right, so last time we were discussing rotations in 3 dimensions. And we showed that the classical transformation that gives you rotations in 3 dimensions is given by the rotation of an observable by a vector angle theta, that is a magnitude theta about an axis in 3 dimensions you define. This is performed by the generator, the Poisson bracket, with the angular momentum vector, dot product with that rotation angle vector, transforming the original observable omega naught. And we wrote down the corresponding quantum transformation with the angular momentum operator. So omega hat of theta vector is e to the minus I over h bar commutator with angular momentum operator dot theta omega naught. Continuing that expression, we have omega of theta equal to, if you open up the commutator, you can write this as e to the plus I over h bar L operator dot theta, omega naught e to the minus I over h bar L operator dot theta. And we said that this is equivalent to these operators being the unitary operator that performs a rotation by the angle theta on the quantum states. And this one then correspondingly is the adjoint Pythagorean. So then the rotation of a quantum state psi of theta is obtained by letting that unitary operator act on it. Okay, so in this way, we showed that the algebra of the angular momentum vector is what controls the behavior of rotations in 3 dimensions. So this is all encapsulated in the algebraic statement of the commutator relations. Commutator of component Li with component Lj is IH bar sum over k epsilon ijk Lk. And we said that this algebra is characteristic of all generators of rotations. And this includes even rotations that do not look like angular momentum. So at the end of this period, whether it's within the scheduled hour and 15 or whether it's in bonus overtime, I will discuss the extension of this to finite dimensional representations and spin. And the bottom line is that any operator that obeys this commutation algebra characteristic of generating a rotation looks and acts like an angular momentum. Acts like angular momentum even if not R cross P. Okay, so with the commutation relations in hand and understanding how the rotations transform scalars, vectors, and tensors, it was easy to see that a scalar operator, like the total angular momentum squared, is invariant under rotations. And therefore it commutes with each of the generators of rotations. And so that means that we can simultaneously diagonalize the scalar L squared and one component of the vector L. The different components of L do not commute with each other, so we can't diagonalize them all, but we can pick one, which we conventionally choose to be the Z component. So the simultaneous eigenstates of the magnitude of angular momentum and LZ will have some value for the total angular momentum L squared, and the magnetic quantum number whose eigenvalue is mh bar for LZ. And the last thing that we did before we wrapped up class last time was we looked in more detail at this commutation relation. We said LZ commutes with LZ squared. LZ also commutes with the perfect square Lx squared plus Ly squared. And just like we did with the harmonic oscillator, we thought it would be useful to factor that into a combination Lx plus or minus Ly. And we saw that the algebra of these linear combinations of Lx and Ly looked a lot like the commutation relations of the raising and lowering operators of the harmonic oscillator. Sorry, other way around. And this smelled awfully familiar to something like A dagger A, commutator with A dagger, gave plus A dagger, and so A dagger acted like a creation operator or a raising operator on the ladder of harmonic oscillator states. And likewise, A dagger A with A gave minus A, and so that acted as a lowering operator. And so it looks very much like the algebra of angular momentum is going to follow in the same spirit as the harmonic oscillator, that we're going to have a ladder of angular momentum states. So let's see how that works. So following this commutation relation, we can show that these do in fact act like raising and lowering operators. So if I have an eigenstate of Lz, if I have Lz and then follow with L plus or L minus, I can do both at the same time. Using the commutation relation, I can switch the order. L plus minus Lz, and I pay the price of the commutator on the state M. When Lz acts on the state M, it just returns mh bar. The commutator of Lz with L plus or minus is plus or minus h bar, and the same operator L plus minus back. So this is plus minus h bar times the same operator L plus minus on M. And now this is just a scalar quantity, and both of these terms have the same operator L plus or minus acting on M. So this gives me M plus or minus 1 h bar times L plus minus acting on the state M. And so the implication is that this state is proportional to the eigenstate m plus or minus 1, because it has the eigenvalue m plus or minus 1. L plus or minus acting on m is equal to some coefficient times m plus or minus 1. So these really are raising and lowering operators the same way that they were for the harmonic oscillator. Okay, so we see L plus and minus act as raising or lowering operators on Lz. But of course, they don't do anything to L squared. These things are just made out of Lx and Ly, and L squared commutes with both of them. So if I have commutator of L squared with L plus or minus. This is just commutator of L squared with Lx plus or minus I Ly. And both of those commutators just give 0. So these are operators that change the z component of angular momentum while leaving the magnitude of angular momentum unchanged. So we know how to solve the system like this. We already did it for the harmonic oscillator. The key is to start with a ground state, a state that cannot be lowered further, and then you can generate all of the higher states by applying the raising operator. But there's one important difference between the angular momentum ladder here and the ladder of phonon excitations or vibrational states that we had for the harmonic oscillator. That difference is that the harmonic oscillator had a floor, a vacuum of phonons, but there was no ceiling. You could always add another vibrational mode. In this case, the total amount of angular momentum is fixed. So it should be intuitively clear that you've got a maximum and a minimum value for Lz. There should be a floor where Lz is taking up all of L squared and it can't get lowered anymore. There should also be a maximum where Lz is as high as it can go and I can't raise it anymore. So the difference is that this ladder of states is finite. There's a floor and a ceiling. And mathematically, that comes from the requirement that Lz squared is positive and Lx squared plus Ly squared is positive. So this thing is bounded. We said Lx squared plus Ly squared. Say I take any expectation value of this. This thing has to be positive, can't be negative. But it also has to be less than the total L squared of the entire system. So this combination, which is what we use to build up L plus and L minus, is bounded below and it is bounded above. That's how you're going to get a floor and a ceiling. So this is equivalent to saying that Lx squared plus Ly squared is equal to L squared minus Lz squared. Both of those terms are positive. And so if I apply this operator, or equivalently this operator, to one of these eigenstates, then I find that it's got to be positive definite. So if I have L squared minus Lz squared, and I sandwich it between eigenstates L squared m, L squared m, then this combination must still be positive, because this number must be greater than 0. That's equivalent to saying that these things are perfect squares and that the magnitude of this vector cannot be negative in the vector space. So since this thing must be positive, that tells me the constraint on the eigenvalues. L squared acting on this combination just gives me the number L squared minus Lz squared is m squared h bar squared, greater than equal to 0. And this gives you the intuitive floor and ceiling of the ladder that you would expect. Your z component cannot be greater than the total magnitude of angular momentum, either positive or negative. M squared h bar squared less than equal to L squared, or m h bar less than equal to L greater than equal to minus L. Okay, so aside from that difference that this ladder has a ceiling as well as a floor, all of the structure that we use to solve the harmonic oscillator will still work for us. We know now that there's a maximum and a minimum state. So there is a value m max. So the ceiling L squared m max cannot be raised. That tells us that L plus acting on that state has to give me 0. And likewise, the floor cannot be lowered. So L minus acting on L squared m min must also be 0. Okay, so let's work out the implications of both of those conditions. So if I have L plus on L squared m max equal to 0, if I hit both sides of this equation with L minus, then I get L minus, L plus, L squared m max is equal to 0. But L plus and L minus were constructed in the first place so that when you multiply them, it gives you L squared, Lx squared plus Ly squared up to a commutator. So when I plug this back in, I get L squared minus Lz squared, that's the Lx squared plus Ly squared part, minus h bar Lz, that was the part that came from the commutator, acting on L squared m max. 0. And this state is an eigenstate of all of those operators. So when I plug this in, I get L squared minus m max squared h bar squared minus m max h bar squared L squared m max equals 0. This is just a combination of numbers. That coefficient must be equal to 0. So I find that L squared, that eigenvalue, is equal to m max plus 1 h bar squared. That's the ceiling condition. Likewise, we can work out the implication of the floor. The floor condition is that the floor cannot be lowered. L minus on L squared m min must be equal to 0. So now if I hit both sides with L plus, I again build back that perfect square up to a commutator. So this product is equal to L squared minus Lz squared. Now instead of minus h bar, I get plus h bar Lz. And again, this gives me the constraint on the eigenvalues. L squared minus m min squared h bar squared plus m min h bar squared L squared m min is equal to 0, and equating the coefficient to 0, I get L squared equals m min minus 1 h bar squared. And since both the ceiling and the floor are set by the eigenvalue of L squared equals this, L squared equals that, they are equal to each other. So that gives me m max plus 1 h bar squared equals m min minus 1 h bar squared, We can clean it up a little bit. The h bar squareds are now unnecessary. This is m max squared. If I subtract from the right, I have m min squared. And then I have plus m max minus m min equals 0. Plus m min. And then this is a difference of squares. These are ordinary numbers. There's no commutation relations. I plot an overall factor of m max plus m min. From this first term in brackets, I have m max minus m min. And then this is just plus 1. So that product is equal to 0, and I've got two possible solutions. Either m max equals negative m min, or m max equals m min minus 1. This second condition is obviously nonsense. This would give me a maximum which is smaller than the minimum. So throw this out. And the conclusion is this one, that my ladder is symmetric, and the maximum value and the minimum value, the ceiling and the floor, are equally spaced about 0. So this is telling me that there is a symmetric ladder around 0. So at this point, it's convenient to rename that maximum and minimum values since they're just differing by a minus sign. Let's call them L, little l. This will be the angular momentum quantum number. And this is telling me that m, the z component of angular momentum, can go from minus L plus 1 up to L. And this constraint here, so I erase the one for the minimum. If I go back and I write that constraint for the maximum, we said L squared was equal to h bar squared, m max is L, m max plus 1 is L plus 1. And so this little l is the angular momentum quantum number. So if I rewrite my eigenvalue conditions in terms of the quantum number L instead of some generic eigenvalue L squared, we get the more familiar form L squared on the state Lm is h bar squared L plus 1, Lm, Lz, Lm is mh bar Lm. Everybody good so far? This is largely a repeat of what we did for the harmonic oscillator. I hope silence means yes. Okay, just like we did for the harmonic oscillator, we can use the raising and lowering states to construct the entire ladder in between, starting with either the floor or the ceiling.
So, little question, please. I'm sorry.
No, please ask a question.
L squared is its effect is to increase the total angular momentum, but Lz is to go within this L squared.
I think most of what you said is correct. So L squared does not increase the total angular momentum. L squared measures the total angular momentum. And yes, Lz raises or lowers within that range of angular momentum. So there's a nice plot. I think I showed something like this when I made PowerPoint slides at the beginning of the class. that you'll have some picture of a sphere that tells you the radius of that sphere is controlled by the angular momentum L. And in quantum mechanics, you have specific discrete states that are allowed here. So you might have, I don't know, plus 3h bar, plus 2h bar. Oh, I don't know. There's 6 of these things. It's supposed to be symmetric about 0. Let me add in one more or something. 3h bar, 2h bar, plus h bar, 0, minus h bar, minus 2h bar, minus 3h bar. So the picture is that there are only certain angles that you can have, and this L plus or minus operator takes you from one of these states up to the other one. But for fixed LZ, the magnitude or that radius of the sphere remains fixed. So you're sort of jumping up and down between different allowed projections of LZ. Does that answer your question?
Yes, but if we increase L squared, is the radius will be more or number of states will be more?
Yes, that's correct. So if you go from quantum number L to quantum number L plus 1, then yes, you increase the size of that ladder. Then now if I go from, this would be the picture for L equals 3. If I go to L equals 4, now there's going to be a new, right, so my radius gets a little bit bigger, all of those lines get a little bit extended, and now there's a new state that you can fit in, plus 4h bar minus 4h bar. So that's what it looks like if you go from L to L plus 1.
Okay.
Maybe this is a good place to point out that the total number of states that exist in the ladder from minus L to plus L is 2L plus 1. There are 2L plus 1 values of LZ that you can have for that fixed value of L squared. Does that answer your question?
Great, thank you.
Okay, awesome. Okay, so to generate the other states, we need to know exactly how L plus or L minus acts on the quantum state Lm. So we need to work out what is the action of L plus on the state Lm. So I'll do this by squaring it. That means I multiply it by L minus Lm, since these guys are Hermitian conjugates of each other. L minus is L plus dagger. So this is, when this acts on the state, this gives me some coefficient C plus times the state L m plus 1. And then this one gives me L m plus 1 times the complex conjugate of that. And we know what L minus L plus is equal to. This, again, if I restore it as the perfect squares, this was L squared minus LZ squared minus H bar LZ. Ln. So evaluating the right side, I get H bar squared L plus 1 coming from LZ squared minus M squared H bar squared minus M H bar squared. If my states are separately normalized, then this inner product gives me 1, that inner product gives me 1, and I just get C plus magnitude squared is equal to H bar squared times L plus 1 minus M plus 1. And up to some complex phase that I can choose to be 0, that coefficient C plus is square root L plus 1 minus M plus 1 H bar. And similarly, we can work out what the value is for the lowering operator. So if I have L minus on Lm squared, this is equal to L squared minus LZ squared plus H bar LZ. And so this gives me the coefficient C minus squared is equal to H bar squared times L plus 1 minus M minus 1. Or again, up to an arbitrary complex base, C minus is square root L plus 1 minus M minus 1, H bar. Okay, and I always forget which ones are plus and which ones are minus. A quick way to check is to say that if you're at the ceiling, M equals plus L, then it should be impossible to raise it. This coefficient should be 0. So if M equals L, that difference is 0, so that's the correct minus sign. And here, if M equals negative L, that should give me the floor, and my C minus should be 0. I cannot lower that state. And again, that also moves. So let me just take notes. This one equals 0 if M equals minus L for the floor. And this one equals 0 if L equals plus M for the ceiling. Okay,
Sorry, I had a question. I can't tell for sure, but it looks like on, like right there in the middle of the board, you have the eigenstate L and then M plus 1, but then you have it equal to, and then the expectation value on the side is only LM, not M plus 1.
Yes.
I think I missed where the plus 1 went.
Right, so two different statements. So one is that L plus is a raising operator, so this one turns M into M plus 1. When I square it, I get the combination L plus L minus, and that combination is related to that perfect square, LX squared plus LY squared. That's what this thing was. And then this one came from the commutator. So these are two different statements, and we're relating them to each other. One is that this thing is a ladder operator that takes M to M plus 1. The other thing is that this is a perfect square, and this is related to the eigenvalues of L squared and the eigenvalues of LC squared. So that's how we figure out, yes, we know this has to take it from M to M plus 1, and the coefficient is fixed based on the eigenvalues of L and M.
Oh, okay, so we just used it to get the coefficient. I get it.
That's right, yeah. So the point is to find the coefficient so that now we have totally determined what the action of L plus and L minus is, and then from that we can build explicitly the entire ladder.
That makes sense, thank you.
Okay, great. Any other questions before we move on? All right, cool. I will erase the middle part of this and try and leave the side. I think I need at least this piece. Okay, so now once we have the overall coefficients, so maybe let me summarize everything here. So we have L plus minus acting on the state ML, LM. It gives us the coefficient, which was L plus 1 minus M plus minus 1, H bar, times the state L, M plus minus 1. Now we've completely determined what that action is. And L plus and L minus are built out of Lx and Ly. So I already know what the eigenvalues of L squared and Lz are. This gives me an easy way to calculate matrix elements of Lx and Ly. So since we had L plus or minus was equal to Lx plus or minus I Ly, then it's easy to invert that equation. You just add or subtract them and divide by 2, and then I get, Lx is equal to 1/2 L plus L minus, and Ly is equal to 1/2I L plus minus L minus. So just like with the harmonic oscillator, when we knew what A dagger and A did, it was easy to plug it back in for X and P. Now we know what L plus and L minus do, it's easy to plug back in and get L plus, Lx and Ly. So for instance, if I want to calculate any matrix element of Lx, L prime, M prime, Lx, Lm. If I plug in this expression, this is 1/2 L prime, M prime, L plus L minus, Lm. And L plus turns the state M into M plus 1 with this coefficient. L minus turns the state M into M minus 1 times the other coefficient. So when I plug this in, I get L prime, M prime, Lx, Lm equals h bar over 2. There was an overall h bar from both coefficients. I've got a factor of 1/2, so I'm going to pull that out front. For the L plus, I get the coefficient for the raising operator, which was L plus 1 minus M plus 1. And then this leaves me with L prime, M prime, Lm plus 1 plus h bar over 2 times the result of the lowering operator, L plus 1 minus M minus 1, L prime, M prime, Lm minus 1. And if these are properly normalized states, then these just give me Kronecker deltas. So this one, for instance, has to be delta L prime L, delta M prime M minus 1. So that element is only non-zero if this thing is 1 lower than that thing. Likewise, this state has to be 1 higher than that. So you get 2 contributions to this. I get h bar over 2, square root L plus 1 minus M plus 1, delta L prime L, delta M prime M plus 1 from the raising part, plus h bar over 2 square root L plus 1 minus M minus 1, delta L prime L, delta M prime M minus 1 from the lower. So you see that the Lx operator is off diagonal. These are not eigenstates of Lx. They shouldn't be. And you see that explicitly because Lx turns one of these things into M plus 1. So if you take an expectation value in the same state, same value of M, you've got to get 0. You only get something non-zero if these guys differ by plus or minus 1. And then you get either this term or that term. Make sense? Hopefully, yes. All right, in the same way, it's straightforward to plug back in for Ly. So I again get h bar over 2. Now I get the square root. Actually, it's h bar over 2i. So I've got the 1 over 2i from the imaginary part. L plus 1 minus M plus 1. We've got the raising operator part. It leaves L alone, and it raises M. Delta M prime M plus 1. And now from this I have minus h bar over 2i for the lowering operator. Again, that leaves L alone, and it lowers M. Okay, so now in terms of these eigenstates, Lm, we know how to calculate the operator action of everything. You can get Lx, Ly, L plus, L minus, Lz, L squared. We've got the whole algebra. Okay, another thing that we can do, just like we did for the harmonic oscillator, once we know what the raising and lowering operators do, we can write them in coordinate space, and we can actually construct the wave functions. Remember that when we did the harmonic oscillator, the first time we did it by brute force. We wrote down a differential equation, we tried to find a series solution, it was a big mess. In the end, we got Hermite polynomials, and when we redid that problem with algebra, we found that we've got a way to create the Hermite polynomials out of these lateral ones. So in the same way, the eigenfunctions, if I take this Lm state and put it in coordinate space, those will be called the spherical harmonics, and the action of L plus and L minus will give us a way to generate the spherical harmonics. These are called the spherical harmonics Y, L, M, and they depend on the spherical coordinate variables theta and phi. This is just the projection of that state Lm onto the coordinate basis theta and phi, i.e. this is just a position vector r where none of this depends on the radial variable in spherical. So for instance, we can write down the action of L plus or minus on the state Lm, projected now onto coordinate space with the angles theta and phi. So let's see, this is equal to theta, phi, this is Lx plus or minus I Ly, Lm. If I plug in what Lx and Ly are in Cartesian coordinates, this is, let's see, y pz minus z py plus or minus I z px minus plus I x pz. Lm. I just plugged in what the angular momentum are. And if this is a position basis, I know what the momentum operators do on a position basis. They become derivatives. So if I let these operators act on that position state, think of this like the position vector r, then this is just equal to, there's an overall minus I h bar because there's one factor of momentum for everything. And then I have y dtz minus c ddy plus minus I c dtx minus plus I x dtc acting on that function, the spherical harmonic. And if I take x, y, and z and I write them all out in spherical coordinates, then I get the totally non-obvious formula. So I don't care so much about this formula. I don't expect you to memorize it. I certainly haven't. But the important thing is that it's a differential equation. And so now if I take the statement, for instance, that if I have the ceiling, L plus on it has to be 0, then that gives me a differential equation where I say this operator with a plus on the ceiling, M equals plus L, gives me 0. And then I can solve that differential equation to derive what the ceiling spherical harmonic is. Likewise, I can demand that the lowering operator L minus on the floor when M equals negative L gives me 0. And again, that will let me derive the spherical harmonic for M equals negative L. So just to give one example, since the ceiling cannot be raised, so here I'm talking about M equals plus L, then this tells me that theta phi L plus acting on the spherical harmonic Lm equals 0. If I plug in that formula, the overall prefactor, since I'm going to put 0 on the right-hand side, this stuff doesn't do anything. Everything in parentheses gives me 0 for the case of plus. So I get d theta plus I cotangent theta d phi y L, and this is for the special value m equals L of theta and phi is equal to 0. This equation is nicely separable. Let's see. So the theta dependence separates from the phi dependence. And my spherical harmonic can be split into a product of a function that depends on theta and a function, an eigenfunction of phi. So we already know that it's an eigenfunction of LZ. And we already found what the eigenfunctions of LZ were. They were e to the im times the azimuthal angle, which in spherical coordinates is phi. So the theta dependence is the non-trivial part. These are called the associated Legendre polynomials. They are polynomials in cosine of theta. So this is often written as PLM of cosine theta. And there are polynomials in cosine theta. So let's see. To make a long story short, if I plug this form in, d phi acting on it just brings down a factor of im. And the theta dependence acts on the Legendre polynomial part, PL. So this gives me dt theta minus, let's see, L cotangent theta, because recall we're talking about M equals L here. Acting on PLL of theta is equal to 0. So if I split this up, this gives me dPLL d theta equals L cosine theta over sine theta, PLL. And if I separate this out, I get dPLL over PLL is L cosine theta over sine theta d theta. And I can integrate both sides. And this gives me PLL of theta is some constant times sine theta to the L. So this is like 1 over sine theta d sine theta. So under substitution, this is d sine theta over sine theta, and you integrate it, you get a log, and then you exponentiate the log. And so you get, this is the form with some coefficient for the ceiling spherical harmonic. And likewise, you can do it for the floor. So this was the Legendre polynomial part. If I plug it back in, then this gives me YLL, the complete spherical harmonic, is some coefficient that's still to be determined, sine theta to the L, e to the IL I. And then I'm not going to belabor the point, but once you have the ceiling, you can generate the entire ladder by acting on it with the lowering operator. And we know what the lowering operator is, that differential form. So if you take that, you hit this with the lowering operator, you will generate YL L minus 1. And you continue the entire way until you hit the floor. So, I don't know, maybe let me just give you the reference in the textbook where these things are written out in more generality. I don't see much benefit to rehashing that here. So on page 335 of the textbook, they have a formula that gives you something like YLM of theta and phi is some coefficients. You have the e to the I m phi that had to be there from LZ. You have something that looks like this. You have sine theta to the minus m, and then you have dd cosine theta L minus m times on sine theta to the 2L, something, again, highly non-obvious. This works for positive values of m. And the negative values of m you can get simply from the positive values. YL negative m is just up to a minus sign minus 1 to the m. YLM complex conjugate. So the coefficient C that I didn't bother writing in detail here, I still didn't bother writing them in detail here, they are chosen so that the spherical harmonics are properly orthonormalized. So if I have integral over the full solid angle, integral d omega, YLM of theta and phi star, YL prime m prime of theta and phi is just the set of Kronecker deltas, L prime L, m prime m, and in case you're not familiar, the solid angle integration here just means integral d phi from 0 to 2 pi, integral d theta sine theta from 0 to pi, and this is also sometimes written integral d phi from 0 to 2 pi, integral d cosine theta from negative 1 to 1. These are all equivalent ways of writing the spherical harmonics. Let's see, so let me also point you to page 337 in the textbook, where they write out the spherical harmonics in terms of the Legendre polynomials. They also write out the first few Legendre polynomials. I don't see much point in rehashing that here. Whew. Okay, man, we are basically out of time already. All right, let's see what I can do in the next 10 minutes, and there's going to be an overtime session about spin, which again is not necessary for the class, just for those who are curious. Any questions about this before I tackle the radial Schrödinger equation? For a Hamiltonian where the potential depends only on the radius, p squared over 2, instead of m, I'll call it mu for the mass to avoid confusion with the magnetic quantum number m, plus v of r depends only on the radial coordinate and not on any angles. This kind of Hamiltonian is rotationally symmetric, and that means that it commutes with the rotation operator. Is invariant under rotations, and therefore it means it commutes with the angular momentum. And since we already know how to find the eigenstates of angular momentum, this means that the Hamiltonian must commute with both the scalar L squared and one component of your choice, which is usually taken to be LZ. So H with L squared is 0, as well as H with LZ is 0. Okay, so that means that we can find simultaneous eigenstates of all three operators, H, L squared, and LZ. So we're looking for eigenstates of the form H, E, L, M, returns the eigenvalue E. L squared on E, L, M returns H bar squared L, L plus 1. And LZ, ELM returns M H bar. Or M going from minus L up to plus L by steps of 1. And since we already know the eigenfunctions of the angular behavior, we know that the state ELM projected onto a coordinate basis must be given by some function of the radius that can depend on the other quantum numbers L and M, although it actually only depends on L, times the spherical harmonics we just found. Okay, so the only piece of new information, the one that's going to determine that radial behavior, is the one that comes from the form of the Hamiltonian itself, i.e. the form of the radial potential. So if I go back to the eigenfunction, or the eigenvalue equation for the Hamiltonian, the Hamiltonian is p squared over 2m, where m is mu, plus v of r, since it's an eigenstate of the Hamiltonian, this is just equal to E times the state back, which is R of R, YLM of beta and phi. And on the right side, I can write this as the differential operator minus H bar squared over 2 mu Laplacian plus V of R, R of R, YLM of beta and phi. Okay, so naturally we express the Laplacian in spherical coordinates, in which case it looks like minus H bar squared over 2 mu 1 over r squared ddr r squared ddr for the radial stuff, plus 1 over r squared times the angular stuff. The angular stuff is 1 over sine theta dd theta sine theta d theta plus 1 over sine squared theta d squared d phi squared. All of this acts on the wave function as well as the potential. So there's V of R, big parentheses, R of R, YLM of theta and phi. Okay, so there's all of this stuff just acts on the spherical harmonic YLM. And when you take all of those derivatives, you very nicely get, let's see, if I multiply everything out, including this factor and this factor, I get h bar squared L plus 1 over 2 mu r squared. And this is just the angular momentum operator. So this is L squared over 2 mu r squared, which is just L squared over 2I. This is the centrifugal barrier in 3 dimensions. This is the angular momentum. This is the moment of inertia. So this is the amount of kinetic energy that the particle must have from its angular structure if it has angular momentum L and z component m. And you see that all that combination of derivatives only depends on L. It doesn't depend on M. And that's because it comes from the spherically symmetric or the scalar quantity, the Laplacian. It doesn't care about C components. It only depends on scalars like L. So if you plug in these quantum numbers L, this equation simplifies an awful lot. You don't have that angular garbage anymore. The radial stuff can also be further simplified if you introduce the radial probability density. So recall that the probability density, the differential amount of probability, is equal to the wave function squared times the volume element, d3r. If I plug in the form of a solution and I plug in the volume element for spherical coordinates, this is r of r squared ylm theta phi squared times r squared sine theta dr d theta d phi. So if I want the radial probability density, I integrate over all the angles, then this is r squared rl of r, integral over the solid angle, ylm of theta phi squared, and the spherical harmonics are normalized so that this is just going to give me 1. So the radial probability density per unit radius, is this radial function r times the volume element, r squared. So, distance squared. So you can think of this as little r times the radial function r of r squared. And this is the natural variable to express the radial Schrodinger equation in. So if I define UL of R is little r to absorb that phase space factor, RL of R, this is the radial probability amplitude. Such that dp dr is equal to U of R squared. In terms of this, the Schrodinger equation looks remarkably simple. Probably over time. Yes, I'm over time. So this is a good point to stop. This is the radial time-independent Schrodinger equation, expressed naturally in terms of the radial probability amplitude. It looks exactly like the 1D Schrodinger equation. With mostly the difference that now you have an effective potential. The effective one-dimensional potential is the actual potential with an extra contribution from the centrifugal barrier. So solving the radial Schrodinger equation in 3 dimensions is not really much harder than solving it in 1 dimension for a 3-dimensional harmonic oscillator, 3-dimensional particle in a box, yada, yada, yada. It just includes the extra effect of the centrifugal barrier in the potential. Okay, so I'm out of time, and I guess that means I stayed up until 1:30 in the morning preparing notes on spin for nothing, but not quite. I'm still going to continue lecturing on the board. I'll split up the video and make a separate video so that those who want to see the part on spin can look it up later. Again, the spin stuff is bonus extra. I will start the semester with that next time, but since I've been aiming for that punchline on spin the whole damn time, I really want to say something about what spin is and where it comes from in terms of angular momentum. Any questions on this core stuff? All right, thank you guys very much. It has really been a sincere pleasure. I've had a lot of fun this semester despite all of the insanity. I hope it's been enjoyable for you as well. I know you guys have other classes you need to run off to. If you are able to and would like to stick around, you are welcome to do so, and I will discuss the origin of spin. If not, the video will be online and you can take a look at it or not at your leisure. Thank you guys very much. Okay, I'm going to pause and unpause the video so that it makes a break in the recording. Okay, so now we're going into overtime, and I want to discuss the origin of spin. So we said that in general, a rotation transforms an operator or some observable based on the following algebraic statement. We said omega of theta some rotation is e to the minus I over h bar commutator of something with a generator dot theta on omega naught, where the generators have a certain commutation relation. And so what we showed already is that when the thing that you are rotating is a wave function, you are rotating the position in space of the wave function, The object that generates that rotation is the angular momentum operator r cross p. So this means I'm taking psi of r, and I'm transforming it to psi of r prime, where r prime is the vector that's been rotated. The generator of this is the angular momentum r cross p. And that is referred to as the orbital angular momentum. And since the momentum operator P can be written as a derivative, or specifically a gradient, you can see that that transformation happens because of that derivative action. It's acting on that argument R and transforming it. So another way to say that is, let's see. That function psi of R just means the projection of some quantum state psi onto the position basis R. And we said that under a rotation, this transforms as e to the minus I over h bar L dot theta, acting on the state psi. The operator L is R cross P. So this is R e to the minus I over h bar. I'm going to write that as theta dot R cross P psi. When R is sitting next to a position eigenstate, it just becomes the eigenvalue R vector. When P is sitting next to it, it becomes minus IH bar derivative. So this is just e to the minus theta dot R dot gradient acting on the wave function psi of R. So this is how you rotate the wave function. Psi of R prime. The action is to take that argument here, take some derivatives of it in a particular combination that rotates that argument to a new position. But that's not the only thing a rotation can do. So I guess the picture that I have that goes along with this is if my rotation axis is this one. So I have a unit vector along this direction, and the magnitude of that vector theta is the rotation angle theta. Then this takes my wave function from being at some point here. This is my psi of R, and it gets rotated to psi of R prime, where that angle, sort of that sweeping out in this 2D plane, is what this action performed by the orbital angular momentum is doing. So if the wave function of your particle is just a scalar, if it's just a single number assigned to every point in space, and telling me psi of R tells you all the information there is to know about that particle, then this is everything that a rotation can do. And there are some particles like that in nature. For a wave function which assigns just a scalar value psi of R to each point R in space, This is all our rotation does. And so for this reason, particles that have wave functions like this are called scalar particles. And famous examples of the scalar particles include things like the pion, which is one of the fundamental mediators of a strong nuclear force, and the extremely famous Higgs boson. But what if your wave function contains more information than that? Holy crap, I burned through the entire packet show. So the important part here is that particles which possess an internal degree of freedom can also be rotated among their components. So the simplest example that I can give is if your wave function is a vector-valued function. So by this I mean my wave function psi is a vector that depends on the vector in space. And I can write that as three components which are themselves scalars. So this could be psi x, which depends on position times a unit vector along x. Psi y, which depends on position times a unit vector. Psi z, which depends on position times a unit vector. So a vector particle, unlike a scalar particle, possesses three internal states, three internal degrees of freedom. And it's convenient to write this as a matrix, so I could write psi of r equals a row vector just made up of the unit vectors I, j, k times the three components. Psi x of r, psi y of r, psi z of r. And so now clearly if the wave function is a vector, as well as depending on space in a vectorial way, now this thing is going to rotate in a more complicated way than a scalar wave function does. In addition to r getting transformed in the way that we already described, I can have a rotation among the components, psi x, psi y, and psi z. And that shows up as a 3x3 rotation matrix acting on those three components. So now there are two aspects. Both r gets rotated to r prime, and psi's components get rotated among themselves. Psi goes to psi prime. So what I mean is that those three components transform as, I'm going to have a new psi prime x, and it's going to be evaluated at a different position, r prime. Psi y prime at a position r prime, psi z prime at a position r prime. The mixing of the components is described by a 3x3 rotation matrix, R 3x3 of theta. Just like we did for a classical vector R that got rotated in 3 dimensions. This is now psi x at R prime, psi y at R prime, psi z at R prime. So there's two aspects going on here. One is the mixing of those 3 components into each other, and the other one is R prime getting transformed. I haven't even written out here how R prime gets transformed. That's what we were already discussing a moment ago in terms of orbital angular momentum. The new aspect here is this 3x3 rotation matrix among the components.
Are they linked? Can you have psi and psi prime rotated without rotating R prime, or vice versa? Or if you rotate one, do you have to rotate both?
You have to rotate both. In order to be consistent with rotational symmetry, you have to transform R prime and psi prime at the same time. Now, maybe your wave function is something that's totally trivial. Maybe psi of R is constant. Then you rotating it does nothing. But you can't have some structure in R prime and rotate the internal degree of freedom and not also rotate the other. All or nothing. Yeah, that's really critical. That's where the total angular momentum comes from. The total angular momentum of the particle is what governs how it rotates, and that includes both the orbital piece coming from transforming R and the spin piece that comes from transforming the internal degree of freedom. So for the moment, I'm not going to worry about the R prime piece. Maybe let's assume that R is just a constant in space. And let's talk only about the effect of this 3x3 rotation. So among those components, I have psi x prime, psi y prime, psi z prime equals a 3x3 rotation matrix for that rotation by the angle theta times the original components, psi x, psi y, psi z. But we've discussed rotation symmetries in such generality already that we know how to write down the representation of that rotation matrix. This is e to the minus I over h bar, some generator, I'll call it S, dot theta. And that acts on those 3 components, psi x, psi y, psi z. It has to be this way if it's going to be a rotation in any sense, in order to be consistent with rotational symmetry. Not only that, I can put constraints on what those matrices are. So these things are some 3x3 matrices. They're 3x3 matrices because they act on a 3-component vector. So there's 2 different aspects of this that I really want to highlight. One is how many components it has, and the other is how many of them there are. So the first statement is that these are 3x3 matrices because they act on a 3-component vector. That shot is totally gone. So the other thing is I write S vector, sorry, this was S dot theta. So the other thing is that there are 3 of them. Sx, Sy, Sz. There are 3 of them because there are 3 directions in which you can rotate. That's different from saying how many components of the thing you're rotating there are. Even when that number is not 3, there still will be 3 of them because there are 3 axes in which to rotate. So there's a couple other sort of conventional properties that we have for S. So one of them is that S has to be Hermitian. So each of the SI's is Hermitian. If it wasn't Hermitian, then this transformation wouldn't be unitary. And the other constraint is that they should be orthogonal to each other. That way you've got three independent transformations. And basically all of these three constraints that are on the board, or all of the constraints on the board, hermiticity being orthogonal, the fact that there are three of them and they are 3 by 3, all of those together uniquely determine what those matrices are up to some overall trivial complex space. And you've already seen what these matrices are. You've done a homework on it. Right, and I didn't even write out the most important constraint, of course, which is that they have to satisfy the rotation algebra. Si Sj is I h bar sum over k epsilon ijk sk. Uniquely determined up to a phase, which is irrelevant. And the matrices that you get are Sx is h bar over root 2. 0, 1, 0, 1, 0, 1, 0, 1, 0. Sy is h bar over root 2. 0 minus I 0, I 0 minus I, 0 I 0. Sc is h bar 1, 0, 0, 0, 0, 0, 0, 0, minus 1. And you can straightforwardly check by multiplying the matrices, for instance, that they satisfy the required properties. Commutator of Sx with Sy is in fact IH bar Sc, as it should be, as per the generators of rotations. So the point is that when you have an internal degree of freedom, there is an extra amount of rotation that is taking place. It's not just the rotation of the position R. It is an additional rotation among the internal degrees of freedom. And that manifests as an extra angular momentum because it takes more to rotate the vector than it did to rotate the scalar. So in words, it appears as an intrinsic angular momentum in a way that we will show in 1 second. Okay, so if I put these things together, now I put the rotation of R and the rotation of the components together, I get the total effect of the rotation on the vector particle. So I have psi prime x of R prime, psi prime y of R prime, psi prime z of R prime. One effect is that I rotate among the components, R3/3 of theta, psi x of r prime, psi y of r prime, psi z of r prime. And then if I also put in the transformation of the position vector r, then this is rotation matrix times e to the minus I over h bar L dot theta psi x of r, psi y of r, psi z of r. And now I can put together on an equal footing both of these effects. The effect of generating this component rotation and the effect of generating that coordinate rotation. So the coordinate rotation, the component rotation was e to the minus I over h bar, that vector of matrices S dot theta, followed by the rotation of the position vector r, e to the minus I over h bar, L operator dot theta. And now we recognize that this matrix and that derivative commute with each other. They have nothing to do with each other because this one is differentiating that R dependence that is the same on all three components. This matrix is rotating those three components no matter what their value of R is. So these operators commute with each other. In other words, this acts only on the internal degree of freedom. This rotates only space. Meaning R goes to R prime. Basically, what I'm justifying is that I can combine those exponents without any cheating because they commute with each other. So the overall effect is e to the minus I over h bar, spin matrix, plus angular momentum operator dot theta, acting on the original wave function, psi x of r, psi y of r, psi z of r. And this is the point, that this overall effect that rotates not only space of the wave function, but also internal components of the wave function, acts like a single combined angular momentum. That is the total angular momentum J of the rotation. So the way I would phrase it is, that this is the total angular momentum necessary to perform both rotations. So J is an operator which acts on the position information. It is also a matrix that acts on the spin component information. And this is equal to the spin matrix plus the orbital angular momentum. So this is what I was saying earlier about you have to treat them both on an equal footing. That you can't just do one without the other. This is how you see that spin behaves like an angular momentum, and it adds together with the orbital part to give you the total angular momentum of the particle. So we've already solved all of the algebra of rotations, and spin is no different. So we know that the scalar s squared commutes with each of the components of s under rotation. I'll use the abbreviation OAM to stand for orbital angular momentum. So in particular, there's the scalar invariant S squared, which is just the matrix Sx squared plus Sy squared plus Sz squared. This is a scalar, and that means it commutes with rotations. So just like we had for orbital angular momentum, we can write down the eigenvalue equations for S squared and for Sz. They look exactly the same as they did before. Right, so this implies S squared commutes with Sc, and therefore they share simultaneous eigenstates. S squared on the magnitude of angular momentum S quantum number, and Sc has eigenvalues h bar squared S plus 1, and Sc just returns h bar Sc. So that magnitude S squared tells you about the total amount of internal angular momentum variables. That's directly measuring how many components there are. So for instance, we already saw that the number of allowed states of Sc, the number of states in the ladder, was 2L plus 1. In this case, it's S. So the number of components that is the number of different Sc values, was 2S plus 1. So if I take the 3x3 matrices that we started off with, I square them and I add them all up. What I find immediately is that S squared for those 3x3 matrices was 2h bar squared times the identity matrix. And so if this is 2S S plus 1, this corresponds to S equals 1. Right? S equals 1, S plus 1 h bar squared, excuse me. This gives me that factor of 2. And that squares with the fact that there should be 2S plus 1, that's 3 components of a vector. So when I say that spin is equal to 1, that is equivalent to telling you that the wave function is a vector wave function. It has 3 components that are being rotated among themselves. So spin 1, i.e. S equals 1, is completely equivalent to saying that you have a vector wave function. Psi of R with 3 components. So the main point that I want to get across here is that this number S, telling you about the total amount of internal angular momentum, is a property of the particle itself. It tells you how many internal degrees of freedom it has. And so you can talk about spin 0 particles, which are scalars, that have no internal rotations. This vector structure is a spin 1 particle. It has vector-like structure and it has 3 components that get rotated in between. Again, there are particles in nature that are vectors. Vector wave functions in nature. You have things like the photon. The photon is a little bit tricky because it's massless, and so it's highly relativistic. That changes the picture a little bit. But there's also things like the deuteron. A proton and a neutron bound together. That's a spin 1 composite particle. You also have things like the W plus minus and Z bosons, which are also vectors. There are lots of vector particles in nature. So this covers almost everything that I wanted to say about spin, how an internal degree of freedom gets rotated along with everything else. since we know the algebra of how rotations work, we can write down all possible generators of rotations and classify what kinds of particles can exist in nature based on the requirement of rotational symmetry. So we know all possible representations of the rotation algebra specifically that commutation relation. Si, Sj equals I h bar sum over k epsilon ijk sk. We did all of that exercise of constructing the ladder operators, solving for the entire ladder structure, so we can write down all possible internal degrees of freedom that can exist in nature. So we already saw that for spin S, i.e. angular momentum L, that there's a maximum to the ladder, Sc max, is plus S. Sc min is symmetric, so that was minus S. And we know that there's an integer number of steps in the ladder. If I start off at the ceiling, I can hit it with a lowering operator L minus n times to get to the floor. So these are related by n operations of the lowering operator. Before we called it L plus or minus, here it's S minus, but it's defined the same way. And so these two statements are connected to each other. That I go from the ceiling to the floor, which is symmetric in exactly n steps. So that tells me Sc max minus Sc min equals n h bar. I go from the max to the min in n steps of h bar. So this was, I guess I should put the h bars with these guys. This is sh bar minus negative sh bar equals n h bar. Or 2s h bar equals n h bar. So the allowed values of the spin are not just integers, but also half integers. 0, 1 half, 1, 3 halves, 2, and so on. So we've seen that spin 0 is a scalar particle. It has 0 internal degrees of freedom. Spin 1 is a vector particle with 3 internal degrees of freedom. It seems like there's something else, a spin 1 half state and a spin 3 half state, half integer states, that get rotated a little bit differently. And these guys are kind of weird. So when classifying all kinds of particles that can exist consistent with rotational symmetry, it seems we have to also include the possibility of a spin 1 half particle. Are valid representations of the rotation group. Where the rotation group for specificity is SO3. So what do these states look like? We said if S is equal to 1 half, the number of states, number of internal degrees of freedom was 2s plus 1. So if S is 1 half, this means that there are 2 degrees of freedom. So these particles are called spinners. And they are 2-component wave functions. So your state psi of r, it's a vector in 3 dimensions, but it's only got 2 components. So there's psi plus of r and psi minus of r. Again, we know how the r dependence gets rotated by orbital angular momentum. So let's just pay attention to the 2 by 2 rotations. among the components. So I have psi plus prime, psi minus prime is obtained from a 2x2 rotation matrix of the original psi plus and psi minus components. Again, we know everything there is to know about the rotation groups. We know how to represent this. This is e to the minus I over h bar, a spin matrix, which is 2x2, dot product with theta, on those original components. And now, just like with the spin 1 case, we can constrain what those matrices are. They have to be 3 matrices, Sx, Sy, Sz. There have to be 3 of them because I have 3 axes to rotate around in 3 dimensions. But now the matrices themselves are 2x2. Because now I'm rotating a 2-component spinner, 2 internal degrees of freedom. And all of the other properties from before still have to apply. They have to be Hermitian, they have to be orthogonal, and most importantly, they have to satisfy the rotation algebra. And just like in the 3-dimensional case, for a spin 1 vector, for a spin 1/2 spinner, those constraints uniquely determine the matrices. And I bet you can tell me what they are. They are the 3 Pauli matrices. So one has the S matrix for X, Y, and Z is just H bar over 2 times the corresponding Pauli matrix. So Sx is H bar over 2, 0, 1, 1, 0. Sy is H bar over 2, 0 minus I, 0. Sz is H bar over 2, 1, 0, 0 minus 1. And you can quickly check that they do satisfy the rotation algebra. Commutator of Sx with Sy is I H bar Sc as it's supposed to be. All of this is well and good, and it looks exactly like what we did before for spin 1, but there's one extra wrinkle that comes in with the Pauli matrices that lets you simplify them. Pauli matrices have the nice property that they are all roots of unity. If you take any of the Pauli matrices and you square them, you get the identity matrix. An equivalent statement is that I can take any unit combination of them. So if I take the Pauli matrices as a vector, dot product with any unit vector n, and I square that, I still get these for any unit vector n. It's just a straightforward exercise. You plug in n's in terms of sines and cosines, and you see that it still works. Because this thing squares to give you 1, that means that we can actually write out the full exponentiator rotation matrix very simply. Normally, it's difficult to write that in closed form, but for the Pauli matrices, we can. So this means when I have psi plus, psi minus prime, and I say this is e to the minus I over h bar s dot theta, psi plus, psi minus. Now I plug S in terms of the Pauli matrices. It's h bar over 2 times the Pauli matrices. So this is e to the minus I over 2. I'm going to write that as theta the magnitude. I'll write it as a unit vector n dot sigma. Psi plus, psi minus. Because I know something about that n dot sigma when it relates to the Pauli matrix. So what does this exponential do? Remember, it's defined by its Taylor series. E to the minus I over 2 theta n dot sigma is defined by sum from j equals 0 to infinity, 1 over j factorial, minus I theta over 2 to the j power, n dot sigma to the j power. And the simplification comes in because every time I have more and more of these powers, whenever I get 2 of them, it squares to 1. So any even power is just the identity matrix. Equals 1 if j is even. If it's odd, I have 1 extra power left over and all of the other factors are squared and they give me 1. So this equals n dot sigma if j is odd. So I split up the Taylor series between even terms and odd terms. The even terms come with the unit matrix, and they also come with alternating powers of -1 because I always get even powers of I. So if I group all of the even powers, I start with 1, and then I have minus 1 over 2 factorial, theta over 2 squared, plus 1 over 4 factorial, theta over 2 to the 4th, plus dot dot dot, times the identity matrix. For the odd powers, I have an extra factor of I left over. I have an extra factor of n dot sigma left over. And then after that, it's just a Taylor series in the angle theta. It has only odd powers. So I have theta over 2 minus 1 over 3 factorial theta over 2 cubed plus 1 over 5 factorial theta over 2 to the 5th plus dot dot dot. These Taylor series in parentheses are just ordinary sine and cosine, where the angle is theta over 2. So this expression gives me cosine theta over 2 times the identity plus I sine theta over 2 times n dot sigma. So because the Pauli matrices are roots of unity, it's actually possible to take that entire rotation matrix and completely evaluate it in closed form. And then we can see exactly how a spinner transforms under a rotation. Psi plus, psi minus equals, I evaluate that entire rotation matrix and I just get something times the identity and something times n dot sigma. So we can write the entire thing in closed form. And now I can give you the punchline about what is so weird about spinners, which is that under a complete rotation by an angle of 2 pi, they are not invariant. So if I plug in theta equals 2 pi, I get sine of pi plus sine of pi is 0. So this whole piece is 0. I also get cosine of pi. Cosine of pi is -1. So a spinner under one 360-degree rotation transforms psi plus, psi minus into negative psi plus, psi minus. So the statement is that a spinner rotates like a Mobius strip. If you take it and you rotate it all the way around, it comes back to you upside down. It flipped by an overall minus sign. And that is quite bizarre. That is a feature that is only possible in quantum mechanics. Because if the wave function psi were an observable, the observable would not be consistent with rotation symmetry. You could rotate it by 360 degrees and your observable would change. That would break physics. But since the wave function itself is not an observable, especially the phase of the wave function is not an observable, if it changes by a minus sign, the probability distribution, which is the wave function squared, is still invariant. So this is something that is only possible in a quantum universe, where the dynamics of quantum mechanics are happening at the level of an amplitude, a probability amplitude. But the observables are happening at the level of the amplitude squared. It's a uniquely quantum feature. And it is made possible by wave-particle duality at the amplitude level. And so we showed that spin 1/2 particles, these spinners, have this weird behavior under rotations that they change by a minus sign because they are special quantum objects. All of the half-integer spin solutions do the same thing. All of these things can be formulated concretely in terms of the group theory that underlies all of this. It might be worth giving you the term associated with this. The special representations of this group that are not invariant, but they are invariant up to a minus sign, are called the projective representations of it. Those are the ones that are invariant up to a minus or up to a phase. Okay. And with that, I give you, my friends, we have constrained God because we have identified all possible symmetries of nature that are consistent, all possible representations that are consistent with rotation symmetry in 3 dimensions. In 3 dimensions, the only particles that are allowed to exist are the following. So we have S equals 0, which are the scalars. And examples of these were the pion and the Higgs. We have spin 1/2, which are called spinors. Examples include the electron, the proton, and quarks. We have S equals 1, which are the vectors. These include things like the photon, the deuteron, the W and the Z bosons. S equals 3 halves, I don't know of any snazzy name for them. I looked up an example, so this includes, what was it? Oh, the delta baryon. This is just an excited state of the proton. And if you continue on down the line, you even get to things like S equals 2. S equals 2 is called a tensor particle, and this is where a hypothetical graviton would live. But we're not really sure if that works. But if there is a quantum graviton, it is a spin 2 tensor particle. And by structuring all possible representations of rotational symmetry in this way, we have a rigid classification system of all particles that can exist in nature that are consistent with the symmetries of space. This structure can be extended to relativity, and then you can constrain all particles that can exist consistent with the symmetries of Lorentz spacetime, and still the picture remains. So I may have exaggerated a little bit when I made that buzz line about constraining God, but this is really a mind-blowing statement to me, is that we have identified all possible representations of rotational symmetry, and anything in physics that can ever be consistent with rotational invariance must fall into one of these classes. That is an unbelievable, mind-blowing statement. So I'm happy to leave it here. Thank you guys very much for sticking around for this. I will post the video online for anybody who is not able to watch this live. If you guys have questions, comments, whoa, what does it all mean, implications for me? All right, thank you guys very much. It's been a real pleasure. Take care. I will see you next Thursday. If you have questions, happy to go through things for the final, work out some examples that might be useful to you for the falls or for the comprehensive exam. Thanks, folks. Take care.
Thank you, Professor.